All right, here are solutions for quiz 2 for Math 213. What we're doing in the first problem here is we're describing the symmetries, so rotational and reflective, of a rhombus. And then it gets at, are your answers the same for any rhombus? If not, describe the possibilities. What I'm getting at there is really, for the sake of symmetries, there's two different types of rhombuses. Rhombi? I should look that up one of these days and figure out if that's the plural. There is a non-square rhombus. Rhomboid, I think maybe that's called. And then there's a square. So square is just a special type of rhombus, because a rhombus is just a shape with four sides that all happen to be the same length. And that happens in a square for sure. But your symmetries are going to differ in these two cases. So if you have a non-square rhombus, you have a rotational symmetry. Maybe symmetry, rotational symmetry, sure. 0 degrees and 180 degrees. You get the 0 degree one for free, that'll always be true. But the 180 degree one, that's special to a rhombus. And you can kind of see that this vertex would sort of flip up to there, and this would kind of flip down to there. If you rotate, flip is a bad word to use, but you could rotate this thing halfway around and it would land right on top of itself. So you have these two symmetries. What about reflection? Maybe I'll draw the lines of reflection. It's tempting to put one right here, kind of going this way, but the problem with a line of reflection going that way is... Sorry, I had to pause that for a minute. I think I was talking about lines of reflection. There is not a line of reflection connecting midpoints, opposite midpoints. There's not a line of reflection right here or right here. I think it's easier to see why this one right here doesn't work. With this one right here, this point would kind of flip up here. That wouldn't work. What about this way? Well, it's kind of the same idea. If you could sort of turn your head sideways and make this flat with your line of vision, you could sort of see how it wouldn't work out. However, there are lines of symmetry that poorly drawn there across the diagonals. Two reflective, sure. Two reflective symmetries over the lines drawn above, sure. Although we get there and there. What about for a square? Because again, a square is a special type of rhombus. So when I just talk about the symmetries of a rhombus, I don't know if I'm talking about this one or this one. So I guess I should describe these. Well, these are a little bit easier as long as you recognize the square as a rhombus and you consider this case in the first place. Rotational, we get 0 degrees. We always get that one. 90 degrees, 180 degrees, and 270 degrees. So we have 4 rotational symmetries. What about reflective? Well, it turns out we have 4 of those as well. 4 C lines above. Sure. We can reflect over that line, reflect over this line, reflect over this line, or reflect over this line. And those are poorly drawn, but basically connect the midpoints, either of these two sides or these two sides, or the diagonals, these or these guys. So those are all your symmetries. Okay, moving on. Oh, this problem. I don't know how this problem's going to go, but I guess we shall see. Okay, so all of these are these, and all of the, okay. Briannas, sure. All Briannas are Briannos. All Briannas are Briannese. Briannese can be Briannas or not. Briannas can be Briannese or not. Okay, it might help to see a bit of a diagram. So I have Briannese and I have Briannos. One way I can picture this is all Briannas are Briannos. So these could be Briannas, and then these could be Briannos. All Briannas are also Briannese. So these could be Briannese. Sorry for being so obnoxious with these names. Okay, so I had to change this a little bit. I think I want this to be Brienne's and these to be Brienne's. So what I'm saying here in the second sentence is Brienne's, these guys right here, could be Brienne's or not. So you could be in here or in here. And similarly, Brienne's, this circle right here, could be Brienne's, so in this circle or not. So all of this information is just describing a situation like this. And what we're supposed to do is figure out what shape these guys could be. Well, let's see. I could say that Brienne's are rhombuses and Brienne's are rectangles and Brienne's are squares. And it would follow a diagram just like this. But there's more options in terms of what I could do. So maybe I'll change colors to present that. I had a similar diagram to this in the worksheet that we saw when we said that Brienne's were, or I could have this be a rhombus, because a rhombus is something that is a kite and a parallelogram. So sort of the idea there is, here's all my parallelogram shapes that have two sides parallel to each other. Some of those have all four sides equal length, which is what you get when you have a rhombus. And then here are my kites. And kites are shapes that have two pair of adjacent equal length sides. And so sometimes each of those pairs will also be the same, in which case all four side lengths are the same, in which case I have a rhombus in here. So I think this is another possibility here. And I think there's even a third possibility that has to do with triangles. In the triangle case, the picture looks a little bit different, so maybe I'll just go back to the text and note that all equilateral triangles are isosceles, because an isosceles triangle has at least two sides equal length, and equilateral has all three. So if you have all three, you definitely have at least two. So all equilateral triangles are isosceles. All equilateral triangles are acute triangles. Because if you're equilateral, it turns out all your angles are the same, and if all of your angles are the same, they all measure 60 degrees, and if they all measure 60 degrees, none of them can measure more than 90 degrees or more. So they're acute triangles. So let's see. All equilateral triangles are isosceles triangles. All equilateral triangles are acute triangles. Acute triangles can be equilateral triangles or not. Is that true? Yeah, I think that's true. Equilateral triangles, isosceles triangles, can be acute or not. Is that true? Yeah, you can imagine a isosceles triangle that's acute, but also one with like a really long base that would not be acute. So maybe I should have written these down here. Brienne's, which in this example are equilateral. Man, this is hard to keep track of all these guys. It's easy. All the word that ends in A are the word that ends in O. All the word that ends in A are the word that ends in I. And let's see if we can get those last two sentences from that. Now I'm saying the word that ends in I, acute triangles. Acute can be the word that ends in O, which is isosceles, or not. Yeah, that makes sense. And the word that ends in O, isosceles, can be the word that ends in I, acute, or not. Yep, those are all true statements. Therefore, I could have Brienne's be equilateral. So maybe I'll write my answer down here. Brienne's are equilateral triangles. Brianne's are acute triangles. And Brianne O's are isosceles triangles. So I think that works as an answer. So either 1, 2, or 3 should work as a solution.